All right, starting chapter 6, section 6.1, the unit circle. Okay, so the unit circle gets its name since it has a radius of 1 unit. The unit circle is also centered at 0, 0, the origin, but that fact doesn't show up in its name. If you remember equations of circles, the unit circle, it's centered at 0, 0, so this is x minus 0 squared and y minus 0 squared, and then this is the radius squared. Okay, so we're going to find some points on the unit circle. In particular, we're looking for the points, and this means the xy pairs that are on the unit circle and have x coordinate equal to a half. So in the picture, here's x equal a half, so we're expecting a point up here on the top half of the circle and also a point somewhere down here on the bottom half of the circle. Okay, so this phrase that the points are on the circle means necessarily that when we plug into the equation for the circle, we'll get equality. So we know the x coordinate. We're being given that as a half, and what we're going to do is solve this equation for the y coordinates. Okay, so I guess we could square out the half, and then we'll subtract the 1/4 over. So y squared will be 3/4, and then we'll take the square root, and we get two solutions here. This is the square root of 3/4 and plus and minus, and then to make this look perhaps a little bit more familiar, I'm going to go ahead and simplify this. When we take the square root of the denominator, we get 2. Okay, so the 2 points specifically are the 2 points. Again, these xy coordinates, not just the y coordinates here, are half comma root 3 over 2. That's the one up on top, and half minus square root 3 over 2. That's the one down on the bottom. Okay. So we'll be looking at several other interesting points on the unit circle. Okay, we're going to talk about terminal points now, and a terminal point on the unit circle is obtained by starting at 1, 0 and traveling a certain distance along the circumference of the circle. So we're going to travel a distance t along the circumference of the circle, and where we stop, this point is called the terminal point for the number t. Okay, so it's important to think here now of t as being a distance, how far you walk along the unit circle. Right? And if the t happens to be a negative number, what we're going to do instead of going, counterclockwise, we're going to go clockwise if t is negative. We will go actually a distance of absolute t if t is negative, but we'll travel in the clockwise direction. Again, this is bringing us to what's called the terminal point for the number t. Okay, so look at a few examples here. We're going to find terminal points for numbers t, that is distances that are a multiple of pi over 2. Okay, well, to do this, what we're going to remember is that the circumference of a circle is given by 2 pi r. And we'll also have to remember that for the unit circle, it gets its name because its radius is 1. So the unit circle has a circumference of 2 pi. Okay, so this allows us to figure out the terminal points, say for, well, let's do pi first. If we travel a distance of pi along the circumference, we get exactly halfway around the unit circle. And so the terminal point for pi is -1, 0. Okay. If we travel, say, a distance of pi over 2, we'll go 1/4 of the way around the circle, and we'll wind up at 0, 1. So the terminal point for pi over 2 is 0, 1. Okay. Terminal point for 2 pi is traveling all the way around, and we get back to 1, 0. Terminal point for the number 2 pi. Okay, so we'll also look at a couple of examples here where we have either a large value for our number t or a negative. So if the number is 3 pi, so again, this is a distance that we're going to travel. We go all the way around once, that's 2 pi, and then another pi will take us halfway around and bring us to the terminal point -1, 0. So the terminal point for 3 pi is -1, 0. And if we look for the terminal point of negative pi, again, we're going to travel a distance of pi, absolute value of negative pi, but we're going to go in the clockwise direction this time. Right, so this is the distance that we travel, and it brings us to the terminal point -1, 0. So the different numbers can lead to the same terminal point on the circle. Okay, we'll look at terminal points for a pi over 4 and multiples of pi over 4 now. Okay, so the idea here is that we're going to travel a distance pi over 4 along the circle, and that's halfway up to the top here. That was a distance of pi over 2. So if we go halfway, by the symmetry of the circle, it says we should be at a point that's on the line y equal x. Okay, so the graphic is already giving us the answer here. What's going to turn out to be the answer will be root 2 over 2 comma root 2 over 2. But to show that, what we're going to do is solve this system. This red dot is on the graph of both the unit circle and the graph of y equal x. So if we solve this system, we'll learn what points there are that are on both of these graphs. And in fact, we will get 2. There's another point down here. Okay, so without further ado, what we're going to do is, in the first equation, we're going to replace the y with the x, because the second equation is saying that y and x are the same. Okay, so what does that tell us? It tells us that 2x squared equals 1, x squared equals 1/2, and this will give us, the two possibilities that x is plus or minus square root of 1/2, and square root of 1/2, if you multiply top and bottom by square root 2, well, I don't know if it's simpler, but it's another expression. You get root 2 over 2. Okay, so that's what the possible values of x are, and then by virtue of the fact that the points are on the equation y equals x, when x is equal to positive root 2 over 2, so is y. So we get root 2 over 2, root 2 over 2, or maybe a copy paste will make this go faster. Or the possibility that x was equal to negative root 2 over 2, and when that happens, y is also negative root 2 over 2. Okay, the answer though, for the reference number, for the number pi over 4, the terminal point is root 2 over 2 comma root 2 over 2. Okay, so here's some other familiar terminal points. So in the previous chapter, we focused on these special angles, and we typically use the symbol theta for an angle. So we looked at the pi over 6, pi over 4, and pi over 3 angles. And now what we're going to do is look at the distances on the unit circle that are those numbers. So there's a connection here. If the circle that we're working on is a unit circle, that is a radius 1 circle, the radian measure for this angle theta is exactly equal to this distance t that you travel along the circumference of the circle. And it's for that reason we have these old friends showing up. These numbers, root 3 over 2 and 1/2 and root 2 over 2. Okay, so it is, I would say, hard not to continue to think about these numbers as being angles, but in our current context, they are in fact distances that we travel along the unit circle. So when we travel a distance of pi over 6, we wind up at this point, and the x and y coordinates are root 3 over 2 comma half. If we travel a distance of pi over 2, we wind up at this point, and the terminal point there is 0 comma 1, straight up point. Okay, like I said, it's hard not to continue to think about t as being an angle, but we do our best. We say, now this is a distance that we travel along the unit circle. Okay, nonetheless, this memory aid that I suggested to you, I think is still quite effective. That when we look at these numbers t, we can think about them associated with an angle, and so we can still think about the steepness of that angle, and then just try to remember that as the angle gets steeper, the y coordinate is getting bigger, and as the angle gets steeper, the x coordinate gets smaller. Right. So hopefully that helps you visualize or potentially memorize this picture in the first quadrant. Now, as always, I guess I tell you, you'll be taking exams at home. You have access to your notes. You can just print this out and have a reference. But in your calculus class, your instructor will expect you to know these values, so you should try to make an effort to get them memorized now. Okay, so now we're going to look at terminal points in other quadrants, and the idea here is to figure out these other terminal points by using the symmetry of the circle. So for pi over 4, when we travel this distance, we're supposed to try now to have it memorized that the terminal point is root 2 over 2 comma root 2 over 2. If we travel pi over 4 in the other direction, well, what we see by the symmetry here is that the x-coordinate for p should match the x-coordinate for q, but the y-coordinate should be the opposite. Right? We're directly across the x-axis. So the terminal point for negative pi over 2 is going to be root 2 over 2 comma negative root 2 over 2. Same x-coordinate, but opposite y-coordinate. And here's another example. If we travel pi over 6 in the counterclockwise direction, we'll wind up being exactly opposite to where we wind up if we travel negative pi over 6, negative 5 pi over 6 in the clockwise direction. Right? These two numbers, pi over 6 and 5 pi over 6, they add up to pi. So these points are directly across from one another. There's a straight line from P to Q. It would pass right through the origin. And what that means is for the point P, it has the opposite x-coordinate and the opposite y-coordinate. So the terminal point for minus 5 pi over 6 is going to be negative root 3 over 2, comma negative half. Okay, so we're going to take these two examples and make hard and fast rules about them. We'll just generalize them into rules that work for other cases too. Right? To do this, what we're going to look at is what's called the reference number. So the reference number for a value of t is the distance along the unit circle from the terminal point for t to the x-axis. So here's the picture. We have this number t takes us a certain distance along the unit circle, and the reference number for t is this remaining distance to get us down to the x-axis. So this would be the t bar, the reference number for t. So if this is our t, if we overshoot the x-axis, we sort of went too far here, then the reference number becomes the distance back to the x-axis. So this would be the reference number, t bar. So reference numbers are always positive. CRT, we get almost all the way around, but we come up a little short, so the t-bar, the reference number, is this additional distance that we have to go now to the positive x-axis. Okay, so yeah, so the same idea here, but just with numerical values. If t is 5 pi over 6, right, we almost made it to 6 pi over 6. The remaining distance that we needed to travel here was pi over 6. So that's the reference number for 5 pi over 6. Maybe I should write one of these down. Reference for 5 pi over 6 is pi over 6. Here's another example. We travel 7 pi over 4. We come up a little bit short. The remaining distance that we would need to travel is pi over 4, so that becomes the reference number. If we go in the negative direction, negative 2 pi over 3, this means we're traveling clockwise. The reference number, well, the distance, the additional distance that we needed to travel was pi over 3. So that's the reference number here. Not negative pi over 3, but pi over 3. And I guess the overshooting possibility here, if we look for the reference number for 5 pi over 4, we went past the x-axis. So the reference number here, oh, I should have had a t-bar on this, is pi over 4. That's the distance along the unit circle to get back to the x-axis. Okay, so last point for, oh yeah, no timestamps today, but it's pretty short, so I think we're okay. What we're going to do now is use reference numbers to find reference points. So here is the three-step process. We're going to get some number t. We want to know its sorry, this is not correct. Something like, we're going to use reference numbers to find terminal points. So we have some number t, and we want to figure out its terminal point. And the way we're going to do it is find the reference number, find the terminal point for that reference number, t bar, and then adjust the signs, the plus and minus signs, to get the terminal point for t itself. Okay, so 3 examples here. So for 5 pi over 6, this is the value of t, and we're looking for the terminal point for 5 pi over 6. The reference number here is pi over 6. That's the remaining distance that we needed to go. So let's do it in the steps that we're supposed to here. So this is part A. I'll do them separately here. So so the picture is telling us that the reference number is pi over 6. For pi over 6, terminal point, and hopefully this comes from, again, memory. This is in the first quadrant. We think about the pi over 6 number. It's shallow. That means its x-coordinate should be quite large. So that'd be the root 3 over 2. And its y-coordinate should be fairly small. So that's the terminal point for 5 pi over 6. And so for, I think a copy-paste might help here. For 5 pi over 6, well, we just have to adjust the signs on the point Q. So what we see is that the point Q is to the left. I'm sorry, the point P is going to be symmetric here. So it's going to be, instead of at pi over 6 here in the first quadrant, the point P that we're after is over here. So it has a negative x-coordinate. Okay, so all we have to do is negate the x-coordinate, and we'll get the terminal point for 5 pi over 6. All right, let's try the others with copy-paste. Maybe that'll speed it up. In the picture for part B, 7 pi over 4 is the value of t. The reference number is pi over 4. Okay, so we try from memory to come up with the terminal point for pi over 4. And that's up here. And now we make the adjustment. The point that we actually want, instead of at pi over 4, it's down here in the 4th quadrant. And so the adjustment that we need to make is in the 4th quadrant. The y coordinates are negative. Right. One more, and then we're done for the day. C. So our initial number is negative pi over 3. The reference number, negative 2 pi over 3. The reference number is pi over 3. Okay, so again, think about this in the first quadrant. That's steep. So steep means the x-coordinate should be fairly small and the y-coordinate should be quite large. Okay. That pi over 3 is over here in the first quadrant, and it's directly across from the terminal point that we want. This terminal point actually has negative x and a negative y. So I'll finish my edits here. Oh yes, sorry, I didn't correctly edit this last example. This should have been a 7 and a 4. This one is a negative 2 pi over 3. And it should, instead of having that, it should have negatives, because both the x and the y are negative. Oh, turning me into a liar here. One last example. If you have a very large value of t, how do you get the terminal point? And the idea here is this large value of t, it's gone around the circle more than once. Now the picture actually tells me that it's gone around 2 times, 2 full revolutions and some more, but typically what you do is just try to subtract off a multiple of 2 pi. So the initial number is 29 pi over 6. If you subtract off 2 pi, that's the same as subtracting 12 pi over 6. And what does that give us? It looks like we get 17 pi over 6, which is still more than 2 pi. So this is just trial and error here. We're going to have to subtract off 4 pi. That'll wind up being 24 pi over 6. And that puts us at the 5 pi over 6 angle. Okay. So after having made that adjustment, now we get the reference number t. That'll be the pi over 6. And then we get the point q, the terminal point for pi over 6. This is shallow angle, so the x-coordinate is big, the y-coordinate is small. And then we make the sign adjustment. Our point is in the 3rd quadrant. I'm sorry, the 2nd. And so we need to negate the x-coordinate for this point. And our final answer here will be the terminal point for 29 pi over 6 is negative root 3 over 2, comma 1/2.